Wonderful, thank you. Now in there. Okay. Yeah, true. It's like group presentation. Yeah, it is. So which one of them is? We got the intro.
Yeah, we can do the intro.
I think it's F5.
Yeah, I think so. Yeah, it's in Linux. It's F11 here. It says.
Yeah, but it doesn't show.
Okay, you need to do function and that one, I think.
Or I can just go.
Oh, okay. Well done, man.
Yep. So who starts? You can do that order. 7 first, then Thanos. Okay. Let's have research and then we go into development. Okay. Do you want to start? Are you tired? You don't want to start? Okay, we could do Catalina Lewis on the other way, on the backwards, up. Okay? All right. Hi, everybody. I hope you had a very nice lunch at the wonderful restaurant of the university. It's always an interesting cultural experience to eat at somebody else's university restaurant. So we're here today after eating to talk about technology. That's the first work group the fourth work group, but the first work group to actually present today. So the coordinators of the technology work group is Costas and myself, and I'm going to be the guy running the show on the table, and Costas is going to be the guy writing down stuff and getting notes and running around getting things organized. The first thing, our group has the characteristics of have a lot of presentations. We have 8 presentations today, which we cut down into 2 chunks of presentations. One is development, and another is research. Out of a better word for it, we try to group it as everybody who is doing what we would call research in general, or more specifically, and everybody who are working in development, which is they're taking the design further and they're approaching market deployment or general deployment. So because I'm a man of a sheer and very clear logic in my mind, we're going to start the presentation upwards. Katerina goes first.
Hello again. I will present you the design and optimization of an axial flux permanent magnet generator for battery-connected wind electric systems using ferrite and neodymium magnets. How do I? No. How do I change?
You're supposed to go
No.
down. It's not working?
No.
Oh no! Come on. Yes. Sorry. Now it is. Yeah.
So in the beginning of this project, our objective was to optimize the operation of small wind turbines for intermediate technology applications. And the steps that we took was research, problem statement, design, optimization, construction, bench testing, and conclusions. Initially, we created a questionnaire about handmade small wind turbines. It was addressed to users, designers, and manufacturers. And the aim of this questionnaire was to record best practices and common problems that we face, to define the user's profile, and to find out more about the multitude and the success or not of these projects. Here are the main topics of the questionnaire. We had 34 answered questionnaires, and it would be very good if you could answer it as well. Some statistic results from the questionnaire. We can see that the majority of small wind turbines are not connected to the grid. They are located in rural areas. They supply just a small percentage of the total electricity of the user. And the users also use other sources, mostly grid and photovoltaics. These questions were the ones that affected the most the direction of our project. On the right we can see the causes of failures of the small wind turbines, the annual rate, and the downtime in days. The most common causes of failures seem to be the design miscalculations and corrosion of the magnet, both of which have a 20% annual rate. And on the left, we can see which year of operation the failures occurred. It is interesting that the most common cause of failure during the first year of operation is corrosion of the magnet. Wanting to investigate more the magnet corrosion, we focused our research on the generator's magnetic material. During the last decades, the majority of AFPM generators are built with neodymium magnets, which, although very powerful magnets, are associated with several problems. They are very susceptible to corrosion. They have high and unstable prices. There is insecurity in their availability, and they have heavy environmental and social costs. We decided to replace the neodymium magnets with hard ferric. These ferric magnets do not corrode because they are iron oxide already. They are low cost, highly available, and generally more accessible materials. We designed AFPM generators using ferrite of grade C8, and our aim was to achieve efficiency equivalent to that of the neo generators. Our design was based on an existing design of the Rurid group for neo generators, and the main modifications that we did was to increase the number of poles in order to develop a specific power with less turns, which would result in less losses and a better efficiency. And we also used thicker magnets to develop strong magnetic fields without reducing the air gap more. We simulated, using MATLAB and PEN, we simulated AFPM generators for two different magnetic materials, ferric C8 and neodymium N40, and for 4 sizes of blade rotor radii. So we had 8 different configurations. We also ran optimization algorithms with criteria of cost and efficiency, using as variables the magnet width and length. So, in other words, we tried to find the optimal magnet dimensions which would result in a low-cost and highly efficient generator. Here are the optimal magnets per blade rotor radius and for the 2 different magnetic materials. We can see that for ferric, the optimal magnets are generally bigger. We need bigger magnets to achieve optimal operation. And here we see that the optimal ferric generators have a bit lower efficiency and lower cost, but much greater volume and mass compared to the optimal neo generators. So this was expected because we increased the number of poles, so the diameter of the generator was bigger, and also the algorithm shows bigger magnets, which increased further the diameter and the weight of the generators. We also searched a universal optimal magnet for both of the magnetic materials, which would be used in all the range of blade rotor radii that we studied. We call universal magnets the magnets that would achieve optimal efficiency and cost for all the generators if all of them were constructed with the same magnet. And here the configurations using the optimal C8 magnet are compared with the configurations using the optimal magnets that we found before, and we can see that the optimal C8 magnet can be used in all the range of blade rotor radii because it brings very similar results regarding cost, efficiency, mass, and volume. And And the same applies for the N40 universal magnet. We also compared the performance of generators using the universal magnet with generators using the commercial magnet, the magnet that is mostly available in the market. And here we can see that the generators using the universal magnet, it is the red one, have a bit higher efficiency and lower mass and volume, especially as the blade rotor radius increases. And for the bigger blade rotor radius, the commercial magnet results in a generator that is too heavy and big to be handled by an average person. And also for the N40 magnet, again the generators using the universal magnet have a slightly better result, especially as the blade rotor radius increases. So at last, we constructed a ferric generator of 850 watts rated power for 1.2 meter blade. We used the 50 by 50 millimeters magnet because it was the closest that we could find in the market, the closest to the optimal. You can see some parts of the construction process. I would like to mention that we opened holes in the rotors to provide better cooling. We used the vinyl ester resin instead of polyester resin. Inside the resin and around the magnet we placed metal wire to provide reinforcement to the structure. And while casting the stator, we left the ends of the coils out of the resin so that we could perform different connections later during testing. Here, after the construction was complete, it was time to compare the ferric generator with a similar power neo generator, and here are the basic characteristics of the two generators that were compared. Some of the tests that we performed was the no-load test, battery load test. We measured the stator resistance and the stator temperature. We observed that the generators had similar efficiency per produced power. Also the ferric, which was the aim of the project, the ferric generator produces the rated power at higher RPM. It has a bigger stator resistance, and it operates at lower temperature because of the holes that we opened for cooling. So, concluding, there are significant results to replace the neodymium magnet. We found out that with some modifications in the design, it is possible to construct a ferric generator of equivalent efficiency, lower cost, but bigger volume and mass. It is a good practice to open holes on the rotors of large generators to provide better cooling. The universal magnets that we found can operate efficiently in all the range of blade rotor radii, and the commercial magnets are not so efficient for the biggest of the generators. Thank you.
Because we're going to have a section only for questions, we're going to line up all the people who have presented and we're going to hammer them with questions all at once. What I'd like you guys to do, while I'm calling myself up for the next presentation, is to write down your questions before you forget them, right? Write them up before you forget them. Yep. It is. Is it peat? When are they supposed to be in the end?
No, it's the people doing the research.
Happening in Lewis and Costas and Pete.
Oh, sorry.
Yeah. So, where am I? It's me. Take it off. All right. So everybody, hello again. Huh? Control my time. Yeah, hold on. You're doing it? Okay, good. The chicken is over there. All right. So the name of my project is called Modular Power to the People, and it's an open source power electronics project. Good reflex. Well, the context of the project everybody knows. Which is we are all in this community of building DIY wind turbines, going through all the process of building the whole thing by ourselves. But then, what happens why is it jumping? Sorry. Yeah, that's it. The question that happens is, what do we connect between our wind turbine and the charge and the things that we want to illuminate? Well, that's the proposition that I'm here to propose you today, is to do it through a DIY electric system. Because whatever we use in there, it's usually off-the-shelf converters, and if they go bust, we got to buy a new one. But what I would like us to do is to do something. The idea here is to have a converter it's a modular converter composed of a main motherboard, who would just probably be the DC bus equipped with some sensors so you can control the DC bus voltage. And within this motherboard have some sockets which you can easily connect or disconnect, specialized modules which can go into that board. So the idea here is that the motherboard will have this DC bus, will probably have an embedded control system, some sensors, and some sort of intelligent detection. When you connect something into the board's going to engage in a dialogue with the new module, identify it, and the motherboard can use the module's characteristics in order to program its inputs and outputs, like a computer, but for power. But there are challenges, of course, because you need it to be compatible with different power sources. It can be wind power, but it can also be sun. It can also be hydro, whatever other kinds of power that needs to be controlled. And in terms of specialized modules, the challenges are that we're going to have different power electronics topologies. We can have a DC to DC converter. We can have different types of DC to DC converters. We can be talking about DC to AC converters or different types of DC to AC converters. They need to be able to connect to the motherboard and work as they are. So there's a challenge behind that. Let me give you an example, because it's difficult to visualize. The principle here is this. Imagine you have two wind turbines. You have a light bulb and a battery rack. What I propose is that you get the motherboard, you put the racks, you put in the modules that we want to put in, and you connect everything. You can connect some of your battery racks in series, some of it in parallel, it doesn't matter. But you connect everything. The wind turbines go in, energy comes out, and if anything goes wrong, you can still fill up your batteries. You don't lose the whole system. If one of your modules go bust, it's like changing a light bulb. You unscrew the module, and you screw a new module in. And then you can repair the old module. But all this, I want to do it open source. Inspired by Hugh's great example, I would love to have a modular electric system recipe book that people can actually use to build their own. Well, the challenges behind this are obvious, because, it needs to be something that actually withstands the test, like something that's not going to burn when people install it in their place. It needs to be something we're dealing about with the same risks that we have by doing the wind turbines can be kind of transplanted into this. Say the wind turbine, if there's a storm, you have to bring it down, otherwise it can have a mechanical failure can occur. Or this kind of system would be, you have to take care of it to be aware of what you're doing, otherwise you have a fire. Well, that kind of things are going to be in the recipe book, just like Hugh is written on his, saying, well, be careful about what you're saying because there are dangers in the fabrication of these. And so far we've got some funding from the University of Strathclyde. We've got a few thousands of pounds to build some prototypes. And the idea that we're recruiting at this moment some undergraduate students. And what we're trying to do is to build some prototypes, test them on the lab, but then send the prototypes out in the world to be tested in real field and, test them until they die. Why not? But to have some good feedback from people in the field and to put that into, I'll send it to you because that's my point. Our project needs you, all right? We need you to help us with whatever application that you feel like. If you want to help us and you want to host our prototypes, we'd be more than welcome, more than glad to ship it to you. And that's it. So questions please later, but we'll get back to it. Thank you. Yes. Yeah. You're next. Which one is yours? Is Min Vayu?
No, something with ILWP.
Can you see it here? Downwind bamboo. No. Stanos, let's comment.
Oh, the top one. That one.
Sorry, people. You can deduce that from my time as well. Right. So you just switch it here.
Thanks.
Right.
Hi. Okay, I'm going to speed up. So I love wind power. Does two things: field projects and technology projects. I'm going to also spend some time talking about the field projects because it is my feeling that the problems that we face or encounter in the field, we try to find technical solutions from them. So first, we want to hear from the field what goes wrong, and from that try to find them. So I'm going to spend a little bit of time on field projects. We have a few field projects, but I'll only discuss two. Mali, first one we started in 2008. Brazil, that's the youngest one. I had the privilege to, together with Gael César, to go over there and start up that project 2 years ago? 2 years ago. Yeah. But starting with Mali, basically the setup is I got a Dutch team in Holland based who are responsible for technological dissemination, knowledge dissemination, funding, stuff like that. And then we have a partner organization who's based in Mali, Yvonne Gambala. The organization is called Around Baba. And yeah, Yvonne is like the mother of the project and hosts it on a daily basis, and faces all the other non-technical issues like cultural differences and stuff like that. We did a business model study with all the parameters that we could find. There are of course a lot of unknowns, and so I'm really happy to share that with everybody, and also have everybody's input what they think is good and bad of it. But basically what we have figured out now is that we can already beat gasoline in Mali. And Mali is a low wind speed region. Actually, we're going to set up a wind measurement campaign to find out exactly what the wind is. But with the figures, the data we have right now, we can beat gasoline. And with gasoline, I mean the rural gasoline stuff. We cannot beat solar, and I don't think from an economical viability case that we are going to beat solar, because the tendency is that solar is getting cheaper and cheaper. However, our main goal is not to be the cheapest. but to empower the people at the same time. If a blade breaks off, a Malian person can make the blade again. So if you look at the life cycle times and you go into that kind of studies, and we cannot beat the grid, so we only plan to put them in rural areas. This is a group of people, 10 people, to give an idea of the level of education, 5 of them cannot read and write. They can make a wind turbine, but they cannot read and write. Here you see them working. They like to work with their own tools. Maybe something nice to share. I learned this from Leila, from Solar Med 4 years ago. We paint the tips blue. After a while, we can visually check from the ground if they start becoming white again. If they start becoming white again, you know, hey, the tip is starting to erode, maybe I need to protect it. So these little simple things, you know, you can already also enhance the detectability, which I think is also a very important design parameter, if everything goes well or not. I made a special manual. I spent almost 1.5 years learning making these drawings. But I did it like IKEA or Lego. So step 1, step 2, step 3, picture 1, picture 2, picture 3. My French is very bad, and half of them can only speak Bambara, the local African language. But just pointing la la la, not even touching one tool, this group was able to make such a wind turbine in 2 weeks' time. They know how to weld, they know how to do wood crafting. I also give workshops to students, but these people can do better all the skills of handcraft than I can do. So that was really amazing to see how that worked. Some problems that we have, the tools, they're not the latest in the world. Supply chain issues, so it's hard to get the right materials. We have sandstorms and lightning strikes. There are 20 times more lightning strikes than in Holland. We had a volunteer there who stayed for 1 year, and he has serious concerns regarding the wind speed there. Well, Mali is now in conflict, and 2 years ago they had a military coup. And still rumbly. And Ebola. It's of course a very serious issue. Me as a Westerner don't know exactly how dangerous it is, but I'm from nature a very scared person, so when I'm in doubt I don't go. But yeah, it's amazing how bad it can be for a country. They also had droughts, stuff like that. So the solutions that we're going to do is we actually planned to go with Christmas to Mali, but we canceled, basically because we don't feel safe. So to tackle this problem, the way that we go forward for the Mali project is that we're going to do a very, very strong focus on making manuals, making animations, making videos, maybe even making little skills to see if we can make education, we can make it such in digestible steps that even they can pick it up, learning from distance, so via Skype and stuff like that. So that's going to be the strong focus. We're going to put a few meters there. It's always very hard, I think, to find a funder who wants to sponsor for a MedMass campaign. They all want to sponsor a wind turbine for a school. But when you say, I want to know exactly what the wind data is, and also knowing that it's, you see a lot of projects that they start out in wind regimes that are very low. If money was not an issue, I would say first start to measure as soon as possible and then continue. And technology, I'll come back to the supply chain issue in a bit. I'm going to skip the other one during time. But in Brazil, this is our youngest project. It's here in Montes Claros. 2 years ago with the Rio Plus 20, I was invited by my company to play Media Muppet over there for a big bag of money. With that big bag of money, Miguel and Matthias Craig went over. And Gael hosted a workshop, which is, you could already fill a whole presentation with that. But actually this project survived. Second workshop started in Montes Claros. We worked together with a capoeira master guy who's been there in a local NGO for more than 3 decades, so we feel really good, committed that we can work together. Same setup as Mali. Really nice. One of our technology projects is going into wooden towers. For a long time I was thinking, okay, what is the most optimal tower? And then I discovered there is no such thing as an optimal tower. It is very much dependent on the local supply chain of that region where you are, what will come up with the best and robust tower. For Mali, it looks like wood would actually be the best option. We did some calculations, also taking the cost into account. We think if you go for a 12-meter tower, we can be 50% cheaper than steel tower. And this is purely based on the fact that it's very hard to get like gas tubes in Mali. So if you actually find somebody, and if you're in a hurry, and everything below 3 weeks is in a hurry, you pay high prices for it. So the more that you can specialize customize on the local supply chain on that country, the cheaper you can get your whole system. So 2 more minutes to run through it. I work in the big wind industry, so I try to involve all my friends. Within the big wind industry, we have so-called solution owners. That's like we now have like find a specialist. Within internal in the company, we have like a yellow pages. So if I want to know something about lightning protection, I can quite easily find the guy about lightning protection. And also with one step still at the university at TU Delft, I speak to all the professors over there, and students like it. Instead of writing reports and making only calculations, they also like to actually build stuff. So there's a whole win-win situation in that sense. We had a student working on generator modeling, but after seeing this presentation of Katarina, I think, it's so advanced what you already have been doing that we might even have to see if we're going to push this one through, because it's not going by natural anyways. We're playing with Arduino, but I see that other people are also playing with Arduino. For low-budget SCADA systems, we hope to make a low-budget SCADA system with GPRS. We don't go for Wi-Fi, but for GPRS, because in Mali, for instance, we see a lot that for the turbines there, GPRS makes more sense. You put a SIM card in there and you have a better reach. Marco, he will come in 1 hour. He's a bit delayed. Just SMS he will come. He's doing a whole full measurement and benchmarking with stuff, so that he will do a presentation of that. Joost, he lives basically in this wind tunnel. He just finished his PhD. This is the OJF. I also recognize it with the NIL. And I got somebody, Manuel Almeida, from the big wind turbine company that I work for, and he's a guru in simulations and setting up that kind of stuff. So together with 4 students from TU Delft, he's building a model in FAST. FAST is an aeroelastic code that has been certified by Germanischer Lloyd. And what we want to do, I mean, there are many simulation codes, also people here in the room that are working on that. And the thing that we want to do with this is really, till the bare bone, validate it with the wind tunnel. Towers, I have some friends of mine, they don't like wind turbines, but they love towers. So yeah, they're working on, we have a whole bunch of structural engineers that also spend their evenings and weekends and nights looking on towers. And towers are important because they're very expensive, and they also, of course, need to be robust and reliable, otherwise serious accidents can happen. So that's my presentation. Sorry for the delay.
It's okay. We go for Costas next. It's okay.
Which one is yours, Costas?
It's a PDF. Yeah, it's the one. Can I see it here? Can
Can I see it here as well?
No.
No.
Sorry.
Okay. Sorry. Okay, so I will quickly make an overview of the assessment, like all the tests we have done so far, of the 2.4 meter turbine as described in the 2005 manual. It's more or less the same as the recipe book, but there's some modifications on the blades, along with some other generators that we have built here. So the whole assessment is based on the turbine that has been built in most applications, which is the one following the recipe book. We do all the constructions in NTUA so that we can also verify that the construction process is similar as the ones that are in the field, basically by people who are doing this for the first time. And we have built a few machines, and we will see most of the results are from the 2.4 neodymium small wind turbine, but we will see some results from the 1.8 meter diameter with neodymium magnets from the recipe book, and also from 4.3 meter axial flux generator for grid connection that we have designed here. They're all based on the same construction process as in the recipe book. So these are some tests from the generator bench test. You will be probably doing some of that stuff on Thursday. So this is a setup where we have the generator connected to batteries with a certain cable connecting the batteries to the generator. So you see that cut-in is almost close to 110, which is what's predicted by the theory. And so the blue line is the voltage, terminal voltage. So the first part is a straight line where it's just EMF, and then you start having the voltage drop on the stator coils and the cable as current is flowing through, and then you have the red line, which is the line current. Yeah, I think it's only the cutting RPM that we are looking at here, I think. Oh yeah, the other thing is that all of these experiments depend a lot on the state of charge of the battery, and the battery is basically you enter into hell if you start considering the battery. We will talk about that a little bit during the generator tests, but it's something that has given us a lot of trouble in all the modeling that we do, because verifying experimentally is difficult because you actually have to, and we end up having to model the battery as well. But we can talk more about that on Thursday when we look at the simulation models. Another thing that a lot of people are worried, am I going to place the coils in the right position, and if they're going to turn, what's going to happen, and so on. So we have seen that in most generators that we have built, although we kind of take good care to put everything straight, but we don't really make a big fuss about it. The phase difference between the three phases is more or less 120 degrees usually, so that kind of verifies that the stator layout in terms of its geometry is more or less satisfactory. This is the efficiency of the same generator. So it's efficiency against rotational speed. So we see that we are operating at efficiencies close to 85%, and then going down to 80 at RPM that is close to lower wind speeds. So, okay, the efficiency is basically what is coming out of the generator.
Related to calculated power, is that your...
The efficiency is, okay, so the setup, you will do this on Thursday, is a torque meter measuring mechanical power, and then you measure electrical power coming out, so that's the efficiency. It's only for the generator. It's not what goes into the batteries, because that includes the cable as well. And obviously, behind this is the torque versus current graph, which is a straight line. It's the equivalent of the EMF versus RPM. So, once you've got that equation, then you know how that generator is operating throughout any point of operation, basically. So you will be doing that on Thursday as well. We've done some measurements on temperature of the stator. So this is the same turbine, 2.4 meter heat pigot rescue book, and we ran it for 15 minutes at around 800 watts, and the stator went up to 85 Celsius, which is fine. And then there were some other tests with the ferrite generator with the holes for better cooling, for better air circulation, and it does make quite a big difference. So these are some other tests on the same generator, and using different cables to connect to the battery, different lengths. So basically adding different amounts of resistance between the generator and the batteries. This is a little bit what Hugh mentioned in the morning, where he introduced resistance into the connection in order to move at better better points of operation, like try to go closer to the MPPT curve. Yeah. So here you see, so this is the 20 meters, and then it's 80 meters, and then it's 140 meters of cable with the same cross-section. So you see, as you start introducing more resistance into the line, you start moving your power curve towards the right. So basically you're speeding up your rotor. So you'll be producing, for example, 500 watts at a higher RPM if you use the longer cable. So this kind of this concept we have integrated into this software program that we'll look on Thursday, which is the connection of the generator to the batteries. And we try to run an optimization that tells you, what kind of air gap, what kind of cable, to be as close as you can to the maximum power curve, increase the energy production. And it's a low-cost way of doing that. And in the end, you might want to go 100 meters from the batteries, and it turns out that you can do that with a very thin cable because you're introducing resistance, and the whole thing is producing much more energy in the end. Other things that we have seen, we have not really gone into this in detail, but there's a lot of harmonic noise because of the rectifier. It's an uncontrolled bridge rectifier, like really basic rectifier, and then the batteries themselves as well. They introduce a lot of harmonics in the current that creates a humming noise of the generator. A lot of people complain about this. A lot of people don't like this noise, and especially if you have to put a turbine towards the prevailing wind direction, and then you get all the wind blowing the turbine first and then to the house or to the settlement. You can hear the turbine. So one thing we're trying to work on now is to introduce some other electronics with the rectifier, just to see if we can avoid this kind of noise. Okay, so these are some tests in the wind tunnel for measuring the aerodynamic coefficient. We'll be doing that test on Thursday as well. This is not a very good test. We want to do some better ones, but basically what you can see, if you see it's different wind speeds. So the 80 meters per second is the green one, and then you get higher wind speeds. For example, the 9.5 meters per second. So basically, what you will see in small wind turbines is that there is because of the low Reynolds numbers that they operate in, you will see that as you increase wind speeds, the optimum lambda will be moving downwards, and you can have maybe two, like you can go from 6 to 4. It's like a big shift towards the left, and also you will be increasing CP as you increase wind speed. So you might, at 6 meters per second, for example, you might be operating at 0.35, and then you can go to 0.4 at 10 meters per second. So there is an interesting concept that has to do with blade design behind all this that we are still looking into. And there is this guy from João from Portugal. He has done a paper as well on that. It's quite interesting. He didn't come to the conference, but okay. So this is the power curve at the test site. We'll go to the test site on Wednesday. Okay, you've seen a lot of these. one thing that's interesting is that the furling system starts to operate at 6.5 meters per second with just a little bit of an angle, but kind of preparing to reach the maximum at 10 meters per second. This is the efficiency of the whole system, like wind to electricity going into the batteries. So we see that we get high efficiencies, like this is a battery connected system, yeah? So we get more than 30% in these low wind speed regions that we really want our system to be operating efficiently. And then the whole thing drops because of the furling system that is introduced. From 6.5 onwards, you see there is a sharp decline. So okay, this is the annual energy production according to the IC standard. But there's a way to calculate all this with the uncertainties and so on. And this is the database of the test site, and you can see different things by going into this software model, this user interface. So you can see that, for example, if you have a wind gust from 6 to 13 meters per second, you can have a power surge of up to 1 kilowatt, whereas you would be normally operating at around 600. So this is something taken into account when you are designing your dump loads and everything. Maybe not oversize it, but also maybe not downsize it too much. What is the wind speed for the rotor to start from standstill? You need a wind gust of about 4.5 meters per second to get the thing spinning, and then obviously it starts working, and then you can go down to 3 meters per second again and produce power. These are some tests that we've been doing on the furling system. We're going to continue that with Esteban. The curve that we showed before is the purple one, and then we add half a kilo, we add 1.5 kilos and then 3 kilos to the tail. So we see how the furling mechanism changes when the tail gets too heavy. The generator doesn't burn. It's quite oversized for this turbine. Okay, one slide more. This is very interesting. At some point we had severe storms, and we thought, okay, let's not turn the turbine down. Let's not close it. Let's see what happens. And we left it at these kind of values. Like we had 31 meters per second wind gust, average wind speed 82 kilometers per hour for 2 days. So it was just furling constantly. So we managed to get this power curve until 25 meters per second, and it's quite impressive that it's so robust, nothing happens. And okay, then we had some problems with corrosion at the test site. So we ended up having to galvanize the discs and also use vinyl ester, which has much better adhesion to the metals. So now we've been galvanizing the discs, and we have no problems. So if you are in a highly corrosive environment, that would be a very good solution. Ferrite magnets, okay, Katerina talked about that. And then we have also done a hydro application, but we can see that at the lab on Thursday. We can have a look at it. Okay, thank you very much.
All right. So that was the first half of all the presentations. Now we're going to the other half. Tando was mad at me because I jumped him, but no, actually you're right. You're fine, Thanos. You can go ahead, and then we'll call Esteban. Like I said, my logic goes very. Which one is your presentation? There you go. That's one, right?
Yep.
Yes. Okay. So this is my presentation. This is one part of my thesis. It's called DFMA, which is Design for Manufacturing and Design for Assembling. It's an essay for a mass production of small wind turbines. And these are the objectives of my presentation now, is to explain the design for the methods, DFM and DFA. I didn't know them, I didn't learn them during my years at the university. It's a very specific, method. And describe also how integrated design approach has a primary influence to the final product, like that the design is a very strong part of the product. And also show the analysis for the wind turbine and the results. So DFM, the definition is DFM is a method of design for ease of manufacturing of all parts of an assembly that will form a product. It's like an optimization of the manufacturing project. You have to go through all the different methods to create each part, like to have a mold or to have a CNC drilling or a CNC cut for each part. There are various methods to produce things. And DFM is a tool to select the most cost-effective material and process to be used in the production. From the very first point of the production, which is the design of in order to make a product you first have to design. So these are the elements of this method. It's the appropriate process selection, which is the material, the volume, the tolerances, the complexity, the setup cost of each material, and everything, and the expertise according to the people that you plan to cooperate or stuff like that. It's a very vital part to reduce the number of the process stages in order to be more easy to manufacture. Eliminating and combining the processes, reducing setup requirements to use less tools, and optimize the process. To optimize the process, you have to recognize the process limitations. Like as you said before, in some parts you cannot find metal structural elements. You can only find wood, so you have to have that in mind at the design. And to exploit benefits of the process, there are also specific guidelines. There are a lot of this method. These are the guidelines. I think you will get the presentation. I'm not going to read all of them. And I have chosen the two most important, I think, for DFM, which is that the cost effectiveness must be addressed in conceptual design, and the less value engineering must affect not only material and labor costs, rather the whole design concept and material and labor costs, of course. I have to say that this method is like a method that some American people have thought, and all the big master companies use that, like General Electric, Hewlett Packard, and many companies. DFA is the other part of the method, is the part for the assembly, and its definition is a method of design used to minimize total product cost by targeting parts count. You have to have a few parts in order to be more effective according to assembly, and have less assembly time, and eventually less part cost. That's the assembly process. Yes, this is as I told you, it was found in beginnings, this method in the 70s and 80s from two professors, I think, American professors, Duhart and another guy, I don't remember. Manufacturers, and were increasingly turning to advanced automation and highly automated assembly processes to reduce the cost and improve the quality of their assembled goods. It was when the automation kind of really started in the industry, and they made this process to improve the time and the cost of the final product. And as for DFA, these are the guidelines, design guidelines, or design rules. There are certain rules, Next, the systematic methods to analyze the assembly. I've used the Lucas engineering method, which and I've used it for all the parts of the wind of the Pigot the wind turbine, which I've first designed in SolidWorks, and then I did this analysis according to Lucas DFA method, and we'll show you the results next. And the basic philosophy of all approaches is to minimize the number of components and maximize the ease of locating and joining. And on the right you can see at the bottom is the DFM, like the component optimization, and then the assembly, and then with these two you got the whole system optimization for product. These are the DFA principles that you have to have in mind when you design. You have to have in mind that you have to minimize the part count, design parts with self-locating features so that you don't get confused when you assemble each part. It has to be easy and very easy, okay, to assemble. Minimize reorientation of parts during assembly. You have to have a certain orientation for all parts. Design parts for retrieval, handling, and insertion, okay. Emphasize top-down assemblies, standardized parts, minimum use of fasteners, which means that it's better to use parts that you can find very easily and then are not like original equipment or stuff like that. You have to encourage modular design, to design for a base part. To design a base part in order to locate other components is basic for the assembly, and all parts have to be symmetrical. The principle. This comparison between DFM and DFA as for saving and part count reduction. As you can see, if you do a lot of DFA analysis, you get less and less part count reduction, but as for DFM, there is an optimum. You have to find an optimum according to the standards that you have in mind, I explained before. My essay was an analysis for 1,000 Pigot wind turbines per year, and I got index rates for this. I could choose 500 or 100, but I don't know, I was discussing with my professor and I chose 1,000, okay. And okay, this is the exact DFA Lucas method, which are these steps. You follow these steps, and if, for example, you go through functional analysis has, you characterize each part according to this table, and you get a specific rate, and then there's a I don't know, say type, mathematical type, that you get a rate, and then if your rate is good, you go back, you continue, or if it's not, you go back and redesign. That's how it works. I got all these rates of all these tables into Excel, which was pretty easy, and then I got all the parts of the Pigot wind turbine to Excel and got an index rate for each part. It's the same way for DFM Lucas method. That's how it works. For example, here you have a rate for complexity for each part. You can choose impact extraction, sand casting, die casting, forge, press, machine, powder net, or a plastic mold. Again, via Excel, I created a little interface that could easily get the index rate. So these are my results. At first, this is the guide tower the Pigot uses. At first, I designed that. Then I designed a tower that is like that. It went also through finite element analysis, which is my poster. I'm not presenting it now. And the final result, according to DFA, was that. You can see the parts are very reduced, and I even got for the last part very good, better index rates than the guide tower. So it's kind of, according to this method, it was optimized. Okay, this is the Lucas DFM method result. These are its parts. Some of the parts, I have not put all of the table, and the final index rate is the manufacturing rate, which if you can get a cost out of that. It's not a clear indication of cost, it's like only a number, but if you indicate one part of the cost, you can relate it to all the other parts and get a cost, a real cost number. Yes. I've tried for the blades many different types. You can see one. These are all the blades, many different types to make the blades. And the best type for the blades was to make a molded plastic blade. So I designed also a plastic mold for a plastic blade, okay? And for the tower components, impact extraction was the best manufacturing method according to the procedure, okay? And this is all. What the previous component of characters according to the method, okay, this is it.
All right. So now we go to Esteban. It's comment me, right? Which one? No, which one is it? I forget. I already have it. I already have it. I'm a pro. Is it open? Okay. It's thinking.
Maybe it's too long.
Maybe. Yes.